So you know about Newton's three laws of physics, right? First law being the law of inertia. Objects in motion stay in motion until another force acts upon them. The second one being the law of acceleration. An object's net force is proportional to its mass and speed, following the equation force equals mass times acceleration. And the third one being the law of action and reaction. For every action, there is an equal and opposite reaction. Well, what does it actually look like in real life example? I mean, there's no way these rules are used for every instance of motion, right? Right? So in an experiment, I decided to look around my house, find an object that can perfectly show all three laws of motion in action, and another secret that I'll reveal at the end of my experiment. So here are the things we're going to need for this experiment. Hard floor and a bouncy object. I chose the hardwood floor that is in my kitchen as the hard floor, and the object I kinda wanted to use, the bouncy ball, that was in my closet, but I decided not to for some secret reasons. So I went for the Nerf bullet. It's pretty light and has the rubber dome that should be perfect for showing the forces being applied onto the bullet. Now let's do some experiments. So the first rule of motion is the law of inertia. Anything that stays in motion until an outside force acts upon them. Does the Nerf bullet follow this rule? Yes, actually it does. It isn't that clear, but the bullet following is an example of an object in a constant motion, and the outside force counteracting it is the ground, putting it in a complete stop. Now technically I might be lying here just a little bit, but it does stop soon enough. I'll explain why soon. Now the second rule states that an object's force is proportional to its mass and acceleration. Now unfortunately this isn't shown in the footage you've provided very well, so I decided to use the backpack I have used since 6th grade and my pencil box. The backpack weighs a lot more than the pencil box, so this can demonstrate the rule perfectly. I'll be applying the same amount of force to push the objects as well because I don't want to have an inconsistent push force, so as to not fiddle with the results. So let's begin. Pushing the heavy backpack was a struggle with the amount of force I was applying to it, plus the friction-filled carpet. It was slow and required a ton of push force for it. For the pencil box, it was easy and quick. This is because the mass of the backpack was way heavier than the pencil box, and applying the same force to the pencil box, which is lighter, gave it faster acceleration. This is a good example of the second rule being applied to the objects. Does the force depend on the mass and speed? Yes, it does. The last and final rule I'll be discussing is the third law of motion. For every action, there is an equal and opposite reaction. The Nerf bullet I showed you before perfectly demonstrates the third and final motion perfectly. So as the bullet hits the ground, it's applying that force to the ground, and as a reaction, the ground actually gives a force equal to the bullet but in the opposite direction, making it bounce up everywhere like you see here. So, can we confirm that the third rule applies to this object? Yes, it does. Yes, it does. Alright, we've done it. We've got some real-life examples of how Newton's three laws are applied to objects, and we can go home now. Yay! This is the end of the video. Alright, bye-bye. And you can go now. You don't have to do anything else. You're good. How about you eat some grass or something? Uh, uh, um, it's a funny thing. I was kidding. I lied again. I didn't just do Newton's three laws of motion. I also did Hooke's law as well, just to show you the other complexities of an object in question. It doesn't apply to all objects, but it does apply to objects who can deform and are elastic. Fun fact, my physics teacher is not a huge fan of this law, saying that it's the most obvious law, and the equivalent of saying that Andy's law stating the sky is fucking blue. Anyway, Hooke's law states that to stretch or compress a spring by some distance, the force needed is proportional to that distance following the formula. Jeez, what the fuck? What does it say? Hold on. F equal to negative kx. F being the force exerted, k being the spring's constant, a spring or elastic material's stiffness, and x being the stretch or compression distance. Examples of this being a spring. you're on tissue. Basically anything that has an elastic property to them. Like, for example, that one thing that most mills have. For this, I'll be using the spring of a pen to make it jump. I've been doing this since I was like first grade, so I know how to do this. And we'll see if Hooke's law works with this pen. Pen spring is 2 centimeters, and the pen compresses it to 0.9 centimeter, giving it a travel distance of 1.1 centimeters. According to VAIA.com, what kind of company name is that? Vaya. The company. Whoops. The pen spring consistency is 30 newtons of force. I compress the spring, set it on the ground, and then let it jump. Got a max jump height of 6 centimeters. Nothing much. I don't know. Does it follow Hooke's law? Yeah, it does actually. Remember, its force is the force of jumping off the ground, while gravity is acting upon them. So the instant it jumps off, a force is being applied equivalent to the distance of the compression, and the pen stiffens. So Hooke's law checks out. And that's all the laws that will be present in the video. I hope you enjoyed the video as I did making it, dreading the due date. Oh boy, the due date. Ah shit. Remember to do what you love, and see you soon. One more thing before I have to leave. Subscribe now, motherfucker.